Hello, friend. Welcome back. Or if this is your first time here, welcome home. Tonight, look up, not with your eyes just yet, with something quieter, something that remembers how to wonder. Because somewhere above you right now, a star is sending light across the dark, and that light carries a color you were never taught to see. Some stars burn blue cold as winter mornings. Others glow red soft as embers fading in a fireplace. A few shine white, steady as old promises. But here's the strange part. When you were young, someone probably told you stars are yellow, golden dots scattered across the night, like coins tossed into a wishing well. And if you drew a star in school, you likely colored it yellow too. We all did. But if you go outside tonight and really look, if you let your eyes adjust and your mind grow still, you'll notice something unsettling. Most stars aren't yellow at all. So, why do we believe they are? Before we drift into that question, into the science and the silence, I want to ask something small. If you find these quiet journeys comforting, if this voice feels like a companion in the dark, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Think of it as leaving a light on, so we can meet here again when the world grows too loud. Now, let's drift. Light is the only thing stars can give us. They're too far to touch, too distant to visit in a single human lifetime. But they're light that reaches us. It crosses the void, patient and tireless, carrying information, written in wavelengths we barely understand. Scientists suggest that when you see a star tonight, you're not seeing it as it is. You're seeing it as it was. The light from Sirius, the brightest star in our night sky, left its surface 8.5 years ago. The light from Betelgeuse, that reddish shoulder of Orion, began its journey more than 500 years ago, when Leonardo da Vinci was sketching flying machines and wondering about the heavens. But here's where it gets strange. That light traveling all that way doesn't arrive colorless. It arrives drenched in hue, saturated with information about temperature, age, chemical composition. Yet most of us walk through life thinking stars are a single shade, yellow, generic, uniform. As if the universe in all its complexity decided to paint every sun the same. The man who first questioned this assumption wasn't an astronomer by training. His name was William Herschel, and in the early 1800s he was obsessed with light. Not just what it showed, but what it was. Herschel built his own telescopes, ground his own mirrors, and spent cold nights in England mapping the sky with a precision that bordered on devotion. But one afternoon, he did something unusual. He passed sunlight through a prism, splitting it into a rainbow, and then he placed thermometers in each color: red, orange, yellow, green, blue, violet. He wanted to know which color was warmest. What he found changed everything. The thermometer in the red section warmed up as expected. But then, he placed another thermometer just beyond the red, in a region where no visible light fell. And that thermometer, sitting in apparent darkness, grew even hotter. Herschel had discovered infrared radiation light our eyes cannot see, but our skin can feel. He had proven that visible light, the rainbow we know, is just a sliver of something much larger. And if light could exist beyond red, beyond what we see, then what else were we missing? It's easy to assume that what we perceive is all there is. The brain is efficient that way. It takes shortcuts, fills in gaps, smooths over inconsistencies. When you look at the sun, your brain sees yellow, not because the sun emits only yellow light, but because your brain is trying to make sense of an overwhelming spectrum. The sun actually emits all colors of visible light, more or less equally. It's what scientists call white light. But here on Earth, our atmosphere scatters the shorter blue wavelengths, making the sky blue, and leaving the sun looking more yellow by comparison. It's an optical trick, a translation error between reality and perception. Research shows that if you were to see the sun from space outside the filtering lens of our atmosphere, it would appear nearly white. Astronauts describe it this way: not the warm, comforting yellow of childhood drawings, but a fierce, almost colorless white like molten glass. This is the sun's true color. or at least the closest our eyes can come to translating it. But we don't live in space. We live beneath a blanket of air, and that air changes everything we see. Think about how many paintings you've seen of sunsets, Van Gogh's Starry Night with its swirling yellow stars, countless illustrations in children's books where stars are drawn as five-pointed yellow shapes, sometimes with smiling faces. This image, this cultural agreement that stars are yellow, runs so deep that even when we know better, we struggle to see past it. It's as if we've agreed to a collective fiction, a shared dream about what stars should look like. But if you go outside tonight away from city lights and let your eyes adapt to the darkness, you'll start to notice differences. Betelgeuse in Orion's shoulder glows a deep orange red like a dying coal. Rigel at Orion's foot shines blue-white sharp and cold. Sirius low in the winter sky flickers with a diamond brightness almost too white to hold a single color. These are not yellow stars. They never were. We just forgot how to see them. Some believe this yellow bias comes from the sun itself. It's the only star most of us ever notice during the day, and our brain's interpretation of it as yellow becomes the template for all stars. Others suggest it's cultural, a kind of visual shorthand passed down through art and language. In English, we even say the sun is a yellow dwarf star, a classification that reinforces the idea. But the term yellow dwarf is misleading. It refers to a category of stars that includes the sun, but not all of them appear yellow to our eyes. The name stuck anyway, like a nickname that outlives its accuracy. Here's a common mistake people make. They assume that because the sun looks yellow and because the sun is a star, all stars must be yellow too. It's logical in a way. But the universe doesn't care much for our logic. Stars come in a spectrum of colors, each one tied to a fundamental property temperature. The blue stars are the hottest, burning at tens of thousands of degrees. The red stars are the coolest, still unimaginably hot by our standards, but cooler than their blue cousins. And in between, there's white, yellow, orange, a gradient written in fire. William Herschel didn't just discover infrared light. He laid the groundwork for understanding that light itself is a messenger. Every photon that reaches your eye has traveled across impossible distances, carrying a story encoded in its wavelength. That story can tell you how hot a star is, how old what it's made of, even how fast it's moving through space. But first you have to learn to read it. Imagine standing in a dark field at midnight, far from any city. Above you, the Milky Way stretches like a river of light, and if you look closely, you'll see that river is not uniform. Some stars are bright, some dim, some white, some red, some faintly blue. It's as if the universe has painted itself in every shade of heat, every degree of age, and hung the canvas above us for anyone willing to look. The ancient Greeks saw this too, though they didn't understand it the way we do now. They noticed that some stars were steadier than others, that some seemed to pulse or change color over time. They called them asteres planetae, wandering stars, not knowing they were actually planets reflecting sunlight. But they also noticed the fixed stars, the ones that stayed put. And they wondered why those stars looked different from one another. Aristotle believed the stars were made of a perfect, unchanging substance called ether. He thought they couldn't vary, couldn't age, couldn't die. He was wrong, but the question he asked was right. Why do stars look different? It would take more than 2,000 years to answer that question properly, and the answer when it finally came was written in color. You don't need to understand everything tonight. You don't need to memorize names or numbers or classifications. All you need to do is sit with the idea that light, this invisible traveler, has been crossing the universe to reach you. And when it arrives, it doesn't arrive empty. It arrives painted, drenched in meaning, soaked in time. The stars are not yellow. They never were. But we needed to believe they were, maybe because yellow feels warm, safe, familiar. And the real truth is a little colder, a little stranger. The truth is that every star is a different temperature, a different age, a different distance from us. And each one has chosen or been given a color that reflects all of that. Tonight we'll learn to read those colors. We'll learn to see past the yellow, past the assumptions, and into the light itself. Because if you can learn to see starlight as it truly is, you begin to see the universe not as a distant abstraction, but as something alive. Something speaking in a language older than words, light born from fire, color born from heat. And all of it, every single photon traveling toward you right now, carrying a message you were always meant to receive. You just needed someone to whisper the translation. So let's begin with the simplest question, the one that unlocks everything else. If stars aren't yellow, then what decides their color? What force, what invisible hand paints each one a different shade? The answer is simpler than you'd think and stranger than you'd imagine. It's written in something you already know, something you feel every time you stand near a fire or hold your hand above a candle flame or watch metal glow red in a forge. Heat. Pure, invisible, ancient heat. And heat, as it turns out, has a voice. It speaks in color. And in the next part of our journey, we'll learn to hear it. Heat doesn't just warm, it transforms. It rewrites matter at the atomic level, turning solid into liquid into gas, and if you push far enough gas into plasma into light itself. And somewhere in that transformation, something remarkable happens. Heat begins to glow, and the glow chooses a color. You've seen this before even if you didn't notice. A stove burner turning from black to red. A piece of metal in a blacksmith's forge shifting from dull gray to orange to yellow to white. Even a candle flame, if you look closely, burns blue at its base and yellow at its tip. Different temperatures, different colors, always, without exception. This isn't poetry, this is physics. And it's the key to understanding why stars wear the colors they do. In 1893, a German physicist named Wilhelm Wien sat down with a problem that had haunted scientists for decades. If you heat an object, any object, it will eventually start to emit light. But why does the color of that light change with temperature? Why does red come first, then orange, then yellow, then white, then blue? Wien worked through the mathematics, the relationships between energy and wavelength, and what he discovered became known as Wien's law. It's deceptively simple. The hotter an object gets, the shorter the wavelength of light it emits most strongly. Short wavelengths are blue, long wavelengths are red. Temperature writes color in a language that never changes. Here's where it gets strange, and this is where most people stumble. We think of blue as cool, ice is blue, water is blue, winter mornings feel blue. But in the language of stars, blue means heat, intense, violent, unimaginable heat. A blue star, something like Rigel in the constellation. Orion burns at around 30,000 degrees Kelvin at its surface. That's more than 5 times hotter than our sun. Meanwhile, a red star, something like Betelgeuse, also in Orion, burns at only 3,000 degrees. Still hot enough to vaporize any material we know, but cool by stellar standards. Blue screams, red whispers, and everything in between hums at its own frequency. Think about the last time you lit a gas stove. If you have one, you've seen this principle in action. Turn the knob and the flame ignites. At first, it might flicker orange, contaminated by dust or impurities in the gas. But when it settles, when it burns clean, the flame turns blue. Not because blue fire is cooler, but because it's hotter. The blue part of the flame, down near the burner, is where the gas mixes most efficiently with oxygen, where combustion is most complete, where temperatures peak. Move your hand above the flame into the yellow or orange region, and it's warm. Move it into the blue, and you'll pull back fast. Blue fire bites. This is the opposite of what our instincts tell us. We've been conditioned to associate blue with cold, red with warmth. Traffic lights, weather maps, cultural symbols, they all reinforce this idea. But the universe doesn't care about our conditioning. In the cosmos, blue is fury. Red is exhaustion, and white sits somewhere in between, balanced, steady, neither screaming nor fading. Let's take this further. Imagine a blacksmith heating a piece of iron. At room temperature, the iron is gray dull, unremarkable. As the blacksmith pumps the bellows and the coals grow hotter, the iron begins to change. First it glows a faint red, barely visible in daylight. The red deepens, becomes orange, then yellow. If the blacksmith keeps going, if the forge burns hot enough, the iron will turn white, almost too bright to look at directly. And if hypothetically the forge could reach tens of thousands of degrees, the iron would glow blue. Each color marks a threshold, a specific range of temperature. Red might mean 1500 degrees Fahrenheit, yellow 2000, white 3000, blue even higher. The iron isn't choosing to be red or yellow, the heat is choosing for it. Stars work the same way, just on a scale so vast it's hard to hold in your mind. A star is essentially a ball of hydrogen and helium, compressed by its own gravity until the core reaches millions of degrees and fusion begins. That fusion releases energy, and that energy travels outward through layers of plasma until it reaches the surface and radiates into space as light. The surface temperature, not the core temperature, determines the color we see. And that surface temperature depends on the star's mass, its size, and its age. Here's a fact that surprises most people. The hottest stars are not the biggest. In fact, some of the largest stars, the red supergiants like Betelgeuse or Antares, are among the coolest. Their surfaces are so far from their cores, so expanded and diffuse, that they cool down to a mere 3,000 or 4,000 degrees. They glow red soft and dim relative to their size. Meanwhile, smaller, denser stars, packed tight with mass, burn hotter and shine blue. Rigel, for instance, is a blue supergiant. It's large, yes, but its surface blazes at 12,000 degrees, 3 times hotter than Betelgeuse, and it pours out far more light. If you could somehow stand on a planet orbiting Rigel, the sky wouldn't just be bright. It would be searing, drenched in ultraviolet radiation, hostile to anything we'd recognize as life. Scientists suggest that this inverse relationship, bigger stars sometimes being cooler, comes down to structure. A red supergiant has expanded so much that its outer layers are barely held together by gravity. Heat dissipates, the surface cools, but a blue star, even a massive one, is still compact enough, still dense enough that its surface remains scorching. It's counterintuitive, but the universe is full of counterintuitions. That's part of what makes it beautiful. Now, let's talk about something you can test yourself. If you have access to a simple household item, an incandescent light bulb, the old-fashioned kind with a visible filament, you can watch Wien's law in action. Plug it into a dimmer switch. At the lowest setting, the filament barely glows. If you look closely, you'll see a faint red, almost invisible. Turn the dimmer up, and the filament brightens, shifts to orange then yellow. At full power, it glows a warm yellowish white. The filament's temperature is rising, and with it, the color shifts towards shorter wavelengths. It's a miniature star, right there in your living room, obeying the same laws that govern Rigel and Betelgeuse, and every other point of light in the night sky. There's a lesson in this, something deeper than just physics. Heat doesn't lie. You can't fake the color of a star. You can't paint it a different shade or adjust its hue in post-production. The color is the temperature, and the temperature is written into the star's very being. When you look at a star and see it burning blue, you're not just seeing light. You're seeing evidence of violence of hydrogen, fusing at a rate so furious it would consume our sun's entire lifetime fuel in a few million years. When you see a star glowing red, you're seeing something gentler, something that might live for trillions of years, outlasting galaxies, outlasting perhaps even the current age of the universe. One of the most common mistakes people make is assuming that red stars are dying. It's an easy assumption. Red feels like an ending, like coals cooling in a fire pit. And sometimes that's true. A red giant, a star that has exhausted the hydrogen in its core and begun fusing heavier elements, is indeed in its final stages. But not all red stars are old. There are red dwarfs, small stars that were born red, that have always been red, and will remain red for incomprehensible stretches of time. These stars are the tortoises of the cosmos, slow-burning, patient, outliving every blue giant that ever ignited. Red doesn't always mean death. Sometimes it means endurance. Wien's law gives us a formula. Lambda max equals B divided by T. Lambda is wavelength, T is temperature, and B is a constant. It sounds abstract, maybe even intimidating, but what it means is simple. Tell me a star's temperature, and I can tell you its color. Show me a star's color, and I can tell you its temperature. It's a two-way translation, a Rosetta Stone written in heat. Let's take Sirius, the brightest star in our night sky. Sirius appears white to most observers, a brilliant, almost colorless white. Its surface temperature is about 9,400 degrees Kelvin. That places it in the A class of stars, hotter than the sun, cooler than Rigel, and right in the range where stars emit light fairly evenly across the visible spectrum. The result is white, not yellow, not blue, not red, just white, pure and simple. Sirius doesn't need to shout. It doesn't need to fade. It just burns steady and bright, a lighthouse in the dark. Compare that to Antares, the heart of Scorpius. Antares is red, deeply red, almost orange in some photographs. Its surface temperature is around 3,000 degrees. That's barely half the temperature of the sun. But Antares is enormous. If you placed it where the sun is, its surface would extend past the orbit of Mars. It's so large that despite its relatively cool temperature, it pours out thousands of times more light than the sun. Size compensates for coolness, but the color remains red, unmistakably red. A warning, or maybe a lullaby, depending on how you choose to listen. There's something almost musical about this. Each star is a note, and the temperature is the pitch. Blue stars are high notes, sharp and piercing. Red stars are low notes, deep and resonant. White stars, yellow stars, orange stars, they fill in the scale, creating a harmony that spans the entire electromagnetic spectrum. And we, standing here on this small planet, circling a middle-aged yellow-white star, have learned to hear that music. Not with our ears, but with our eyes, our instruments, our equations. You might wonder, does this apply to everything? If you heat anything enough, will it glow blue? The answer is mostly yes, with some caveats. Certain materials will vaporize or break down before they reach blue-hot temperatures. But in principle, in an ideal scenario, any object heated to tens of thousands of degrees would emit blue light. The universe doesn't play favorites. The rules apply to stars, to metal, to gas, to plasma, to anything made of atoms. Heat writes color, and color reads heat. It's a conversation that's been happening since the first stars ignited 13 billion years ago, and it will continue long after the last star fades. Think about what this means for a moment. When you see a photograph of a nebula glowing red and blue and green, you're not just seeing colors, you're seeing a temperature map. The red regions are cooler, perhaps ionized hydrogen glowing at lower energies. The blue regions are hotter, energized by nearby massive stars. The green comes from oxygen doubly ionized, radiating at a very specific wavelength. Every hue is information. Every shade is a clue. The universe is not painted arbitrarily. It's painted by physics, by chemistry, by the fundamental rules that govern energy and matter. So, when you step outside tonight and look up at Orion, see if you can notice the difference between Betelgeuse and Rigel. One red, one blue. One cool and vast, one hot and fierce. They're both supergiants, both nearing the end of their lives, but they've chosen different paths, different temperatures, different colors. And those colors tell their stories more honestly than any words could. Heat writes the color of stars. It always has. It always will. And now that you know the language, you can read the stars not as distant decorations, but as furnaces, each one burning at its own temperature. Each one glowing in the only color it can. Blue for the young and violent, red for the old or the patient, white for the steady, and every shade in between a temperature, a truth, a voice calling across the void. But temperature alone doesn't explain everything. Because stars aren't just hot, they're organized. They fall into families, into classes, into a spectrum so precise that astronomers can predict a star's fate just by measuring its light. And that spectrum, that rainbow of stellar fire, is where we're headed next. There was a woman who spent her life looking at starlight through glass plates, thousands of them, hundreds of thousands. Each plate was a photographic negative, a captured spectrum, a frozen rainbow from a distant sun. Her name was Annie Jump Cannon, and between 1896 and 1940, she classified more than 350,000 stars by hand. She didn't use computers. She didn't have algorithms. Just her eyes, her mind, and a system so elegant it's still used today more than a century later. Cannon worked at Harvard College Observatory in a time when women weren't allowed to be called astronomers. They were called computers, human calculators paid less than their male counterparts, but often doing more meticulous work. Cannon was deaf, partially from a childhood illness. Maybe that's why she could focus so deeply. Maybe silence gave her a kind of clarity the rest of us never find. She looked at spectrum after spectrum, noting the lines, the colors, the patterns, and slowly she began to see something no one had seen before. Stars weren't random. They fell into families, classes, a sequence. She organized them by temperature from hottest to coolest and gave each class a letter: O, B, A, F, G, K, M. At first, the letters were alphabetical, but as the system was refined, some classes were dropped, others merged, and the order was rearranged by heat. The final sequence became a kind of poem, a mnemonic, that generations of astronomers would memorize. Oh, be a fine girl, kiss me. Or in more modern versions, oh, be a fine guy, kiss me. 7 letters, 7 families. An entire spectrum of stellar fire sorted by a woman who couldn't hear but could see deeper into the cosmos than almost anyone alive. Let's walk through that spectrum now, slowly the way Cannon might have, moving from the hottest stars to the coolest, from blue to red, from fury to patience. Each class is a world unto itself, a different kind of sun, a different way of burning. O-type stars are the rarest, the hottest, the most short-lived. Their surface temperatures exceed 30,000 degrees Kelvin. They glow blue, intensely blue, almost violet if you could see them up close. These stars are massive, often 20 or more times the mass of our sun, and they burn through their hydrogen fuel so fast that they live only a few million years. In cosmic terms, that's a blink, a breath. O-type stars flood their surroundings with ultraviolet light, ionizing the gas around them, creating glowing nebulae like the Orion Nebula. They're the rock stars of the galaxy, brilliant and doomed. Examples include Theta 1, Orionis C tucked inside the trapezium cluster, and Zeta Puppis, a runaway star racing through space at over 60 kilometers per second. B-type stars are slightly cooler, but only slightly. 10 to 30,000 degrees, still blue, still fierce. Rigel is a B-type star, and so is Spica in Virgo. These stars are also massive, also short-lived, but they live a bit longer than O-types, maybe 10 to 100 million years. They're still young enough that many haven't even had time to leave the nebulae where they were born. B-types are responsible for much of the blue light we see in distant galaxies. When astronomers look at a galaxy and see blue regions, they know star formation is happening there. Blue means youth. Blue means violence. Blue means time is running out. A-type stars bring us into the realm of white. Temperatures between 7,500 and 10,000 degrees. Vega. The brightest star in Lyra is an A-type. So is Sirius, though Sirius leans slightly toward the blue end. A-type stars are fast rotators, many of them spinning so quickly that they bulge at the equator. They're a few times more massive than the Sun, and they live for about 1 billion years. Still a short life by stellar standards, but long enough to seem almost stable. A-type stars are the balance point, the place where blue begins to soften into white, where heat begins to feel less like an assault and more like a presence. F-type stars are where things start to feel familiar. Temperatures from 6,000 to 7,500 degrees. They glow white with just a hint of yellow, like morning light filtering through a clean window. Procyon, the brightest star in Canis Minor, is an F-type. These stars are only slightly more massive than the Sun, and they can live for several billion years. They're stable, predictable, the kind of stars that might host planets with liquid water, with atmospheres with life. When scientists search for habitable worlds, they often look around F-type stars. Not too hot, not too cold, just warm enough. Then we reach G-type, our home. The Sun is a G2V star, a yellow dwarf, though as we've learned, it's not particularly yellow. Surface temperature around 5,500 degrees. G-type stars are the Goldilocks stars, neither too massive nor too small, neither too hot nor too cool. They live for about 10 billion years, long enough for planets to form, for atmospheres to stabilize, for life to evolve. Alpha Centauri. The closest star system to us is also a G-type. These stars are common, reliable, the backbone of the galaxy. If the universe has a middle class, G-types are it. K-type stars are cooler still, 3,500 to 5,500 degrees. They glow orange, a soft ember-like orange. Arcturus, the brightest star in Boötes, is a K-type giant. So is Aldebaran, the eye of Taurus the bull. K-types are smaller than the Sun, less massive, and they live even longer. Some K-type stars could burn for 20 or 30 billion years, far longer than the current age of the universe. They're dim compared to blue giants, but they're steady, patient. And because they live so long, they give planets more time to develop complex life. Some scientists suggest K-types might be better candidates for habitable worlds than G-types simply because they offer more stability over longer timescales. Finally, we arrive at M-type, the coolest, the reddest, the smallest. Temperatures below 3,500 degrees. M-type stars, also called red dwarfs, make up about 70% of all stars in the galaxy. They're tiny, often less than half the mass of the Sun, and they burn so slowly that they could live for trillions of years. Proxima Centauri. The closest star to Earth aside from the Sun is an M-type. Barnard's star is an M-type. These stars are so faint that none of them are visible to the naked eye, despite being incredibly common. If you could gather all the stars in the Milky Way and sort them by type, the overwhelming majority would be red dwarfs. They're the silent majority, the background hum of the galaxy, the stars that will still be burning long after everything else has gone dark. But M-types aren't just small main sequence stars. The class also includes red giants and red supergiant stars that were once hotter, once smaller, but have expanded and cooled as they aged. Betelgeuse is an M-type supergiant. Antares is an M-type supergiant. These stars are enormous, hundreds of times larger than the Sun, but their surfaces have cooled to red. They're dying, or at least transitioning, and their red glow is a kind of farewell. Not all red stars are the same. Some are ancient. Some were born red and will stay red forever. Here's a common mistake. People see the sequence O through M and assume it's a timeline. They think stars start as O-types and gradually cool down to M-types as they age. That's not how it works. A star's type is determined by its mass at birth. A massive star will be born as an O or B-type and will stay in that range for its entire main sequence life. It won't become a G-type or an M-type unless it evolves off the main sequence and becomes a giant. A low-mass star, on the other hand, will be born as a K or M-type and will remain there burning steadily, never hot enough to climb the spectrum. The sequence isn't a path, it's a sorting system, a taxonomy. Each star is born into a family, and for most of its life, it stays there. Now let's talk about the Sun again, because this is where people often stumble. The Sun is classified as a G2V star. The G means it's in the G-class temperature around 5,500 degrees. The 2 means it's on the cooler end of the G-class, closer to K than to F. The V means it's a main sequence star still burning hydrogen in its core, not yet a giant. But here's the thing. If you could see the sun from space, it wouldn't look yellow. It would look white maybe, with the faintest tint of yellow, but mostly white. The sun emits light across the entire visible spectrum, more or less equally. It's our atmosphere that filters out some of the blue, making the sun appear yellower than it is. On Earth, we see a yellow sun. In space, astronauts see a white sun. The classification G2V is based on the star's spectrum, not on what color it appears to our eyes. This distinction matters. It means the sun isn't a yellow star because it looks yellow. It's a yellow dwarf because of where it falls in the sequence, and even then the term yellow is a bit of a misnomer. Vega is often used as a reference star, a standard against which other stars are measured. Vega is an A0V star, nearly pure white, and astronomers have historically set its color index to 0. Every other star's color is measured relative to Vega. Bluer than Vega gets a negative color index. Redder than Vega gets a positive one. It's an arbitrary choice, but it's a useful one. Vega becomes the anchor point, the 0 degree on the color scale. And from that anchor, the whole spectrum unfolds. Sirius, slightly bluer, has a negative index. Arcturus, much redder, has a positive index. The sun, somewhere in between, sits slightly positive, a hint warmer than white. There's something almost poetic about this system. Annie Jump Cannon didn't know about nuclear fusion when she created it. She didn't know that stars burn hydrogen into helium, that mass determines temperature, that temperature determines color. She just looked at the patterns in the light and sorted them, and her system worked. It still works, because the universe, for all its chaos, follows rules. And those rules are written in color. Have you ever wondered why we don't see green stars? The spectrum goes from blue to red, passing through white and yellow and orange, but green seems to be missing. The reason is subtle. Stars don't emit light at a single wavelength. They emit a broad spectrum, a range of colors, with a peak at a certain wavelength determined by temperature. A star that peaks in the green part of the spectrum, around 5,500 degrees, also emits a lot of red and blue light. When your eye combines all those colors, it sees white or yellowish white, not green. Green is there, but it's always mixed with other colors, and the mix washes it out. It's a quirk of human perception, a limitation of our eyes. The universe isn't hiding green stars. We just can't see them as green because of the way our vision works. The stellar rainbow O through M is more than a classification system. It's a map of possibility. Every star you see, every point of light, fits somewhere on that scale. And once you know where a star fits, you can predict so much about it. Its mass, its lifespan, its fate. You can estimate how bright it is, how far away, what kind of planets might orbit it. The color isn't just decoration, it's data. It's destiny written in wavelengths. Cannon classified stars for decades, most of them, while working in a cold, poorly lit room, hunched over glass plates, her fingers tracing lines of spectral absorption. She published the Henry Draper Catalog, which listed the spectral types of over 225,000 stars. It was the largest astronomical catalog of its kind at the time, and it's still referenced today. Cannon's work wasn't just meticulous, it was foundational. She gave us the language we use to talk about stars, the framework we use to understand them. And she did it all while being paid a fraction of what her male colleagues earned, while being denied the title of astronomer, while working in a field that barely acknowledged her existence. It's easy to look at the night sky and see randomness, a scattering of lights bright and dim with no apparent order. But if you learn to see color, if you train your eye to notice the blues and reds and whites, the randomness dissolves. Patterns emerge, families appear, the stars stop being decorations and start being stories. Each one a temperature, each one a fate. Each one burning in the only color it can, following rules it didn't choose but can't escape. O, B, A, F, G, K, M. 7 letters. A spectrum of fire, a taxonomy of suns. And each class, each family is shaped by something fundamental, something that was decided the moment the star was born, Not by choice, not by chance, but by the one thing that governs a star's entire existence, from the color of its light to the length of its life: mass. The silent hand that writes every star's destiny long before the first photon escapes its surface. And that's where we turn next. Imagine two candles. One is thick heavy, made of dense wax. The other is thin, delicate, barely wider than your finger. You light both at the same time. Which one burns longer? The thin one, of course. It has less fuel. It consumes itself slowly, carefully stretching each gram of wax across hours. The thick candle, meanwhile, burns bright and hot, pouring light into the room, but it won't last. By morning, it will be a pool of melted wax, while the thin candle still flickers, patient and dim. Stars work the same way, but the logic runs backward. The massive star, the thick candle, doesn't burn slowly. It burns faster, hotter, brighter. It devours its fuel at a rate so violent that it will die young sometimes in just a few million years. The small star, the thin candle, burns so slowly it could outlive the current age of the universe. Mass is destiny, and destiny in the cosmos is written in color. In the early 20th century, a British astronomer named Arthur Eddington worked out the mathematics behind this paradox. He discovered what's now called the mass-luminosity relation, a formula that connects a star's mass to its brightness. The relationship isn't linear, it's exponential. Double a star's mass and its luminosity doesn't just double. It increases by a factor of 10 or more, depending on the mass range. Triple the mass, and the luminosity skyrockets even further. More mass means more gravitational pressure in the core, which means higher temperatures, faster fusion, and an avalanche of energy pouring outward. The star doesn't burn longer because it has more fuel. It burns faster because it's crushing that fuel under its own weight. Let's make this concrete. Take Rigel, the blue supergiant in Orion's foot. Rigel has about 21 times the mass of our sun. You'd think that would mean it has 21 times as much hydrogen to burn, so it should live 21 times longer. Right, wrong. Rigel is burning through its fuel so fast at such an extreme rate that it will exhaust its core hydrogen in only about 8 to 10 million years. The sun, with far less fuel, will burn for 10 billion years. That's 1,000 times longer. Rigel is the marathon runner who sprints the entire race and collapses halfway through. The sun is the walker who finishes slowly, steadily, long after everyone else has gone home. Now, compare Rigel to something on the opposite end of the spectrum. Proxima Centauri, the closest star to Earth after the sun, is a red dwarf. It has only about 12% the mass of the sun. 12%. A fraction. And yet, because it burns so slowly, so efficiently, it could live for 4 trillion years. That's not a typo. 4 trillion. The universe is only about 13.8 billion years old. Proxima Centauri, if left undisturbed, will still be burning long after every massive star has died, long after galaxies have merged and dispersed, long after the universe has grown so old and cold that star formation itself has ceased. Small stars don't just live longer, they outlast time itself. Here's where it gets strange, and this is where most people's intuition breaks. You'd think that because Rigel is massive, it would also be cool. After all, it's huge. Its surface is far from its core. Shouldn't that distance allow it to cool down? But no. Rigel's surface temperature is around 12,000 degrees, Kelvin, more than twice as hot as the sun. Its color is blue, white, sharp, and bright. Meanwhile, Proxima Centauri, tiny and dim, has a surface temperature of only about 3,000 degrees. It glows red faint, almost invisible without a telescope. The massive star is hotter. The small star is cooler. Mass drives temperature, and temperature writes color. Blue giants are giant because they're massive, and they're blue because that mass forces them to burn hot. Red dwarfs are small, and red because they lack the mass to ignite hotter fusion. There's a lesson here, something almost philosophical. The brightest stars, the ones that flood the galaxy with light, are the ones that die first. They're spectacular, yes, gorgeous. But they're brief. Blink and you'll miss them. The dim stars, the ones you can barely see, are the ones that endure. They're the silent background of the cosmos, the infrastructure that will hold the universe together long after the fireworks have ended. It's a reversal of what we expect. We think brightness means longevity, that the strongest survive. But in the cosmos, the meek inherit the galaxy. Let's talk about Betelgeuse for a moment, because it's a star that confuses people. Betelgeuse is red. It's also enormous, a supergiant so large that if you placed it where the sun is, its surface would extend past the orbit of Mars. You might assume, given its size, that it's cold. And in a sense, you'd be right. Its surface temperature is only about 3,500 degrees cooler than Proxima Centauri in some estimates. But Betelgeuse wasn't always this way. It was born as a massive star, likely a blue or white giant burning hot and bright. Over millions of years, it exhausted the hydrogen in its core and began fusing heavier elements. As it did, its outer layers expanded, ballooning outward, and as they expanded, they cooled. The surface moved farther from the core, and the temperature dropped. The star turned red, not because it lost mass, but because it changed structure. It's still massive. It's just old. And old massive stars don't stay blue. They swell cool and glow red in their final years. This is one of the most common mistakes people make when looking at color. They see a red star and assume it's small or dying. Sometimes that's true. Betelgeuse is dying in the sense that it's nearing the end of its life. But not all red stars are dying. Proxima Centauri is red, and it's barely started its life. It's young in cosmic terms, and it will stay young for trillions of years. Red doesn't mean old. Red means cool. And cool can come from being small at birth, or being large and expanded in old age. You have to know the context to understand the color. Now, let's flip the question. Why can't small stars be blue? Why doesn't a star like Proxima Centauri burn hot and bright? The answer comes down to pressure. A star's core temperature is determined by how much gravitational pressure is squeezing it. More mass means more gravity, which means more pressure, which means higher core temperatures. Proxima Centauri, with only 12%, the sun's mass doesn't have enough gravity to compress its core to the temperatures needed for rapid fusion. Its core reaches a few million degrees, enough to fuse hydrogen, but not enough to do it quickly. The fusion rate is slow, the energy output is low, and the surface stays cool. The star glows red because it has no choice. It doesn't have the mass to burn hotter. There's a minimum mass for a star, a threshold below, which fusion can't happen at all. Scientists suggest that limit is about 8% the mass of the sun, or roughly 80 times the mass of Jupiter. Below that, you don't have a star. You have a brown dwarf, an object that's too big to be a planet, but too small to sustain hydrogen fusion. Brown dwarfs glow faintly from leftover heat, from gravitational contraction, but they don't burn. They fade over time, cooling into darkness. They're the failed stars, the objects that never quite made it. And they teach us something important. Mass isn't just a number, it's a switch. Enough mass and you ignite. Not enough and you drift dim and silent through the dark. On the other end of the spectrum, there's also a maximum mass, though it's less clearly defined. Stars much more than about 150 times the mass of the sun become unstable. Their cores generate so much energy, so much radiation pressure, that they start to blow themselves apart. Some of these hypermassive stars are surrounded by nebulae clouds of gas they have ejected in violent outbursts. Eta Carinae is an example, a star so massive and unstable that it's experienced multiple eruptions over the past 2 centuries, each one flinging material into space at thousands of kilometers per second. Stars like this don't live long. They can't. They're too massive, too bright, too unstable. They'll explode as supernovae within a few million years, seeding the galaxy with heavy elements and leaving behind neutron stars or black holes. Here's a thought experiment. Imagine you could watch a star from birth to death, but sped up like a time lapse. A massive star, say 20 solar masses, would ignite in a flash of blue-white light, burn brilliantly for a few million years, swell into a red supergiant, and then explode all within the blink of an eye. A low-mass star, say 0.2 solar masses, would ignite as a dim red ember and just sit there glowing faintly for trillions of years. Even if you sped it up 1,000,000 times, it would still look motionless. That's the difference mass makes. One star lives fast, the other lives slow, and the difference is written in color from the very beginning. Let's bring this back to something you can see tonight. Go outside and look at Orion if it's visible in your sky. Find the 3 stars of Orion's belt. Above the belt and to the left, you'll see Betelgeuse glowing red. Below the belt and to the right, you'll see Rigel glowing blue. These 2 stars are both supergiants, both massive, both nearing the end of their lives. But Betelgeuse is cooler, redder, older. Rigel is hotter, bluer, younger. They're siblings in a way, born from the same region of space, but their different masses have sent them down different paths. One is fading into red, the other is still burning blue. And both in their own time will die spectacular deaths, leaving behind either neutron stars or black holes, the final echoes of mass collapsing under its own weight. There's something almost tragic about massive stars. They're born with so much potential, so much fuel, but they squander it. They burn everything they have in a cosmic instant. They don't get to see the slow unfolding of time, the patient evolution of galaxies, the gradual cooling of the universe. They live in fast forward and they die young. Meanwhile, the small stars, the ones we barely notice, will witness it all. They'll see galaxies collide, stars form and die, black holes evaporate. They'll be the last witnesses to the universe, the final candles, flickering in an infinite dark. Does that change how you see them? Does it change how you think about color? Because when you look at a star and see blue, you're not just seeing heat, you're seeing youth, recklessness. A star that chose or was chosen by physics to burn everything it has as fast as possible. And when you see red, you're not necessarily seeing age. You might be seeing patience, efficiency. A star that will outlast empires, species, planets, perhaps even memory itself. Color is fate, and fate in the end is mass. But mass doesn't just determine how long a star lives or how hot it burns. It also determines what happens to the star as it ages, because stars don't stay the same. They change, they evolve, and as they do, their colors shift sometimes dramatically, as if the star itself is trying to tell a different story. That's the journey we're stepping into. Now, the slow, inevitable transformation from one color to another, written in the currency of time. Nothing stays the same. Not people, not civilizations, not even stars. There's a diagram, a map really, that astronomers use to track the life of every star in the galaxy. It's called the Hertzsprung-Russell diagram, named after 2 men who independently created it in the early 1900s. Einar Hertzsprung in Denmark, Henry Norris Russell in America. Neither of them knew at first what they had discovered. They were just plotting stars, graphing brightness against temperature, trying to find patterns. What they found was a map of time itself. On the diagram, most stars fall along a diagonal band called the main sequence. This is where stars spend most of their lives burning hydrogen in their cores, stable and predictable. The Sun sits on the main sequence. So does Sirius, Proxima, Centauri, Vega. But not every star stays there. Some drift upward and to the right, becoming red giants. Others drift downward and to the left, shrinking into white dwarfs. The diagram doesn't just show where stars are, it shows where they're going. And where they're going is written in color, in the slow, inevitable shift from one shade to another, as if the star is aging before our eyes. Let's start with a star like the Sun, because it's the one we know best, the one whose future we can predict with unsettling precision. Right now, the Sun is about 4.6 billion years old, roughly halfway through its main sequence life. It's burning hydrogen in its core, fusing it into helium, releasing energy that travels outward and lights our sky. Its surface temperature is about 5,800 degrees Kelvin. Its color, if you saw it from space, is white with just the faintest hint of yellow. It's stable, reliable, but it won't stay this way forever. In about 5 billion years, the Sun will begin to change. The hydrogen in its core will run out not all at once, but gradually, as the core becomes dominated by helium ash. Without hydrogen to fuse, the core will start to contract under its own gravity. As it contracts, it heats up, and that heat ignites a shell of hydrogen just outside the core. This shell burns hotter and faster than the core ever did, pouring more energy outward. The outer layers of the Sun, responding to this surge of energy, will begin to expand. Slowly at first, then faster. The Sun will swell, growing larger, cooler, redder. It will become a red giant. At its peak, the Sun will be more than 200 times larger than it is now. Its surface will extend past the orbit of Mercury, possibly past Venus. Some models suggest it might even reach Earth's orbit, though by then, Earth will be a charred, airless rock, stripped of its atmosphere, baked sterile by the dying Sun. The surface temperature of this red giant Sun will drop to around 3,000 degrees. It will glow a deep ember-like red, casting a dim reddish light across whatever remains of the inner solar system. The Sun will no longer be the bright, comforting yellow-white star we know. It will be something else. Something older, something ending. This is the fate of every star like the Sun. Every G-type, every K-type, every star that isn't massive enough to explode as a supernova, they all become red giants. It's not a choice. It's a consequence of physics, of the inevitable exhaustion of fuel and the gravitational collapse that follows. And the color change from white or yellow to red is the visible sign of that transformation. The star isn't dying, not yet, but it's transitioning, moving from one phase of life to another, and the color announces the change. But the story doesn't end there. After spending a few 100 million years as a red giant, the Sun will undergo another transformation. The helium in its core, compressed and heated by the ongoing gravitational collapse, will eventually ignite. Helium fusion is different from hydrogen fusion. It's hotter, faster, less stable. The core will burn helium into carbon and oxygen, releasing another surge of energy. The outer layers of the Sun will contract slightly, and the surface temperature will rise again. The star will shrink, brighten, and shift back toward the blue end of the spectrum, though not all the way. It will become a horizontal branch star, somewhere between a red giant and a main sequence star, neither fully old nor fully young. Eventually, the helium will run out too. The core will contract again, heating up, igniting another shell of helium around a now inert carbon-oxygen core. The outer layers will expand again, and the Sun will become a red giant for a second time, this time even larger, even cooler. It will pulsate, shedding its outer layers in gentle waves, creating a planetary nebula, a glowing shell of gas expanding into space. And at the center, left behind, will be the core. A hot, dense remnant no longer capable of fusion, glowing purely from residual heat. A white dwarf. White dwarfs are strange objects. They're about the size of Earth, but with roughly half the mass of the Sun. That means they're incredibly dense. A teaspoon of white dwarf material would weigh several tons. They don't burn. They don't fuse. They just cool slowly, radiating away their heat over billions of years. When a white dwarf first forms, it's hot around 25,000 degrees or more. It glows blue-white, brighter than the Sun, despite being so small. But over time, it cools. The color shifts from blue-white to yellow to red. Eventually, after trillions of years, it will cool completely, becoming a black dwarf. A cold, dark cinder floating through space. No black dwarfs exist yet, though. The universe isn't old enough. Every white dwarf is still glowing, still cooling, still on its way toward darkness. This is the journey of a sun-like star. white or yellow on the main sequence, red as a giant, blue-white as a newly formed white dwarf, red again as it cools, and finally black, a full spectrum lived across billions of years, each color marking a different chapter in the star's long, slow decline. It's not a sudden death. It's a fade, a gradual dimming, a color wheel turning in reverse. Now, let's talk about massive stars because their journey is different, faster, more violent. A star with 10 or 20 times the mass of the Sun doesn't have billions of years, it has millions. And its color changes happen on a time scale that feels almost rushed by cosmic standards. A massive star is born blue-burning hydrogen at a ferocious rate. It stays blue for a few million years, maybe 10, maybe 20, if it's on the smaller end of the massive range. But then, just like the Sun, it runs out of core hydrogen. The core contracts, the outer layers expand, and the star becomes a supergiant. But here's the difference. A massive star doesn't stop at helium. It keeps fusing layer after layer helium into carbon-carbon, into neon-neon, into oxygen-oxygen, into silicon-silicon, into iron. Each stage happens faster than the last. Hydrogen fusion might last 10 million years, helium fusion a million years, carbon fusion a few thousand years, silicon fusion mere days. The star is racing toward an endpoint, and the color reflects that race. As the star swells and cools, it shifts from blue to white to yellow to orange to red. By the time it's fusing silicon in its core, it's likely a red supergiant, enormous and cool, glowing softly in the infrared. And then, abruptly, it dies. The core collapses, triggering a supernova, an explosion so bright it can outshine an entire galaxy for a few weeks. The color of the supernova depends on its type, on the composition of the star, on the physics of the explosion. But for a brief moment, the dying star shines in every color at once, a final burst of light, before it either becomes a neutron star or collapses entirely into a black hole. The journey from blue to red for a massive star is measured in millions of years, not billions. It's a sprint, not a marathon. And the color change is faster, more dramatic, as if the star knows it doesn't have time to linger. Here's a common misconception. People assume that all red stars are old, that red equals the end of life. But that's not always true. Some red stars are old. Betelgeuse, a red supergiant, is ancient by the standards of massive stars nearing the end of its life. Aldebaran, an orange giant, has left the main sequence and is slowly expanding. But Proxima Centauri, also red, is young. It was born red. It will stay red for trillions of years. Red doesn't mean old, red means cool. And cool can come from youth or from age, depending on the star's mass and its history. Let's look at a real example, a pair of stars that show this evolution in action. In the constellation of Lyra, there's a star called Vega. Vega is white, an A-type star, hot and bright. It's young, only about 450 million years old, still burning hydrogen in its core. It will stay on the main sequence for another few 100 million years, maybe a billion, before it begins to swell into a giant. Now imagine if Vega had a twin, a star born at the same time from the same cloud of gas, but with slightly less mass. That twin would evolve faster because less massive stars live longer on the main sequence but transition to giants sooner relative to their total lifespan. By now, that twin might already be a red giant while Vega is still white. Same birth, different paths, different colors. Evolution writes the difference. There's another example closer to home. In the constellation of Gemini, the twins Castor and Pollux tell a similar story. Castor is actually a system of 6 stars, all relatively young and hot-burning white and blue-white. Pollux, on the other hand, is an orange giant cooler, older further along in its evolution. They're not true twins, not born from the same cloud, but their proximity in the sky makes them look paired. And the color difference between them, white versus orange, is a visual reminder that stars age at different rates. That color is a clock ticking at different speeds. Research shows that you can estimate a star's age by looking at its position on the Hertzsprung-Russell diagram. A star on the main sequence is young or middle-aged. A star in the giant branch is old. A white dwarf is ancient, already dead, in the traditional sense, just cooling down. The diagram is a timeline, and color is the marker. Blue giants are young and doomed. Red giants are old and transitioning. White dwarfs are remnants, the final echoes of stars that once burned bright. But here's something that surprises people. Not all stars get to complete the journey. Some stars, particularly in binary systems, have their evolution interrupted. If a white dwarf has a companion star, it can pull material from that companion, adding mass to itself. Eventually, if it accumulates enough mass, it can reignite fusion not in a controlled way, but in a catastrophic explosion called a type Ia supernova. The white dwarf, which had been cooling peacefully, suddenly detonates, obliterating itself entirely. No remnant, no neutron star, no black hole. Just a rapidly expanding cloud of gas and a brief blinding flash of light. The star's color journey ends not in darkness, but in fire. Think about what this means. Color isn't just a passive trait. It's an active record, a living history written in light. When you see a star's color, you're seeing its past, its present, and hints of its future. A blue star tells you it's young, massive burning, fast. A red giant tells you it's old, transitioning, expanding into its final phase. A white dwarf tells you it's finished, cooling, fading. And every shade in between tells a slightly different story, a different moment in the long, slow evolution from birth to death. Can you imagine watching a star evolve in real time? Of course not. Human lifespans are far too short. But if you had millions or billions of years to sit and watch, you'd see the color shift. Slowly at first, imperceptibly, and then faster as the star aged. Blue to white, white to yellow, yellow to red, red to nothing, or blue to red to supernova. Each path unique, each color, a marker, each shade, a message sent across time. The sun will turn red. That's not a maybe, that's a certainty. And when it does, the skies of Earth, if Earth still exists, will glow with a strange, dim crimson light. The oceans will boil away. The atmosphere will strip into space. The planet will become a barren sphere circling a dying star. But by then, if humanity survives, we'll be long gone, scattered to other stars, other systems watching our old home from a safe distance. And maybe we'll look back at the red giant sun and remember when it was yellow, when it was kind, when it gave us warmth and life and light. The color will have changed, but the memory, if we carry it, will remain. Stars age, they shift, they evolve. And their colors, those beautiful varied colors, are the only way they can tell us what stage they're in, how much time they have left, whether they're beginning or ending. But color isn't just about time. It's also about composition, about the invisible fingerprints of elements hidden in the light waiting to be read. And that's where the real detective work begins. Light doesn't just carry color, it carries information, hidden messages written in a code so precise that if you know how to read it, you can tell what a star is made of without ever touching it. You can analyze the chemistry of an object millions of light years away, break down its composition atom by atom, all from the light it sends. It sounds impossible, like magic. But it's not magic, it's spectroscopy. And it began with a German glassmaker who noticed something strange about the sun. In 1814, Joseph von Fraunhofer was working with prisms trying to improve the quality of optical glass. He passed sunlight through a prism, splitting it into a rainbow, and looked closely at the result. What he saw shocked him. The spectrum wasn't smooth. It was interrupted by hundreds of thin dark lines like cracks in a painted surface. Fraunhofer didn't know what caused the lines, but he mapped them carefully, labeling the strongest ones with letters. The D line, the G line, the H line. He spent years cataloging them, measuring their positions, trying to understand what they meant. He died before he found the answer, But the lines he discovered now, called Fraunhofer lines, became the foundation of a new science. Decades later, scientists realized what those lines were. They're absorption lines, gaps in the spectrum, where specific wavelengths of light have been absorbed by elements in the sun's atmosphere. Each element absorbs light at very specific wavelengths, like a fingerprint. Hydrogen absorbs certain colors. Helium absorbs others. Sodium, iron, calcium, each one leaves its mark. When light from the sun's core passes through the cooler outer layers, those elements absorb their signature wavelengths, creating dark lines in the spectrum. The rainbow becomes a barcode, and each line is a clue. Here's where it gets strange. In 1868, during a solar eclipse, a French astronomer named Pierre Janssen and an English astronomer named Norman Lockyer independently noticed a bright yellow line in the sun's spectrum that didn't match any known element on Earth. They called it the D3 line, and they realized it came from an element that had never been identified. Lockyer named it helium, after Helios, the Greek god of the sun. For nearly 30 years, helium existed only in the sun. It was a solar element, something we knew was out there, but had never found here. Then in 1895, a Scottish chemist named William Ramsay isolated helium from a uranium ore sample on Earth. The element that was discovered in the stars finally came home. Think about that for a moment. We found helium in the sun before we found it on our own planet. We decoded the chemistry of a star 93 million miles away before we understood the chemistry of the rocks beneath our feet. That's the power of spectroscopy. It doesn't require proximity. It doesn't require touch. It only requires light. Now, let's talk about how this works, because the mechanics are beautiful in their simplicity. Every atom has electrons orbiting its nucleus, and those electrons occupy specific energy levels, like rungs on a ladder. When an electron absorbs a photon of light, it jumps to a higher rung. When it falls back down, it releases a photon. The energy of that photon, and therefore its color, depends on the distance between the rungs. Hydrogen's rungs are spaced one way. Helium's are spaced differently. Calcium's differently still. Each element has its own unique pattern of energy levels, and therefore its own unique pattern of absorption and emission lines. Light becomes a signature, and the signature never lies. In the early 1900s, a young woman named Cecilia Payne arrived at Harvard to study astronomy. She was brilliant, relentless, and largely ignored by the male-dominated field. But she had access to the glass plate spectra that Annie Jump Cannon had classified, and she began analyzing them in a new way. She applied quantum mechanics, the new physics of the atom, to the spectral lines. She calculated the relative abundances of elements in stellar atmospheres. And what she found was revolutionary. Stars, she concluded, are made mostly of hydrogen and helium, not iron, not silicon, not the heavy elements that dominate Earth. Hydrogen and helium, the lightest elements, make up more than 98% of a star's mass. Her advisor told her she was wrong. Other astronomers dismissed her findings. The prevailing belief at the time was that stars had roughly the same composition as Earth, rich in metals and rocky materials. But Payne stood by her analysis. She published her thesis in 1925, and it was later called the most brilliant PhD thesis ever written in astronomy. She was right. Stars are mostly hydrogen and helium. Everything else, all the heavier elements, carbon, oxygen, nitrogen, iron, are trace impurities, barely a few percent of the total mass. The universe is simpler than we thought, at least in terms of composition. But those trace elements, those tiny fractions, tell enormous stories. Let's focus on a specific example. The Balmer series, named after the Swiss mathematician Johann Balmer, describes a set of hydrogen absorption lines in the visible spectrum. The most prominent is the H-alpha line, a deep red line at 656 nanometers. When you look at a photograph of a nebula glowing red, that red is almost always H-alpha emission. Hydrogen atoms are absorbing energy from nearby hot stars, getting excited and then releasing that energy as red light. The color isn't arbitrary. It's 656 nanometers always, because that's the energy difference between the second and third energy levels in a hydrogen atom. Physics dictates the color. Chemistry writes the script. Sodium is another interesting case. If you've ever seen an old streetlight glowing yellow-orange, you've seen sodium emission. Sodium vapor lamps emit light at 589 nanometers, a very specific shade of yellow. That same yellow line appears in the spectra of some stars, particularly cooler stars, where sodium vapor can exist in the atmosphere. If you see that line, you know the star contains sodium, not because you visited it, not because you scooped up a sample, but because the light told you. The light always tells you. Here's a common mistake people make. They see a star glowing red and assume it's made of something red. Or they see a blue star and think it contains some blue substance. But color doesn't work that way. The overall color of a star, as we've learned, is determined by temperature. The spectral lines, the specific absorption and emission features are determined by composition. A red star can have the exact same chemical makeup as a blue star. The difference is temperature, not chemistry. The lines tell you what it's made of. The color tells you how hot it is. They're separate pieces of information, both written in the same beam of light. Let's talk about something even stranger. When astronomers look at very distant stars in other galaxies, they notice something odd. The spectral lines are shifted, sometimes toward the red end of the spectrum, sometimes toward the blue. This shift isn't caused by temperature or composition. It's caused by motion. If a star is moving away from us, its light gets stretched, and the wavelengths shift toward the red. This is called redshift. If a star is moving toward us, the light gets compressed, and the wavelengths shift toward the blue. This is called blue shift. It's the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it moves away. But instead of sound, it's light, and instead of sirens, it's stars. Edwin Hubble in the 1920s used redshift to discover something astonishing. Almost every galaxy he observed was redshifted, meaning they were all moving away from us. Not just a few, all of them. And the farther away a galaxy was, the faster it seemed to be receding. Hubble realized this meant the universe itself was expanding, that space was stretching, carrying galaxies apart like dots on an inflating balloon. This discovery, made by reading the spectral lines of distant stars, changed our entire understanding of the cosmos. The universe wasn't static. It had a beginning. It was still growing. And we knew this because we learned to read the colors of light. Think about how powerful this is. You can take a single beam of starlight, pass it through a prism or a diffraction grating, and extract a wealth of information. Temperature from the overall color, composition from the spectral lines, motion from the shift of those lines, age, density, pressure, magnetic fields, all of it encoded in light, waiting to be decoded. Spectroscopy is the closest thing science has to telepathy. We don't need to visit a star to understand it. We just need to listen to its light. Let's bring this back to something practical. If you've ever looked at fireworks, you've seen spectroscopy in action. Different chemicals produce different colors when burned. Strontium burns red. Copper burns blue. Sodium burns yellow. Barium burns green. Firework makers use this to paint the sky, mixing elements to create specific hues. It's the same principle astronomers use, just on a cosmic scale. When you see a nebula glowing green, it's often because of doubly ionized oxygen, which emits light at 507 nanometers. That specific green is oxygen's signature, as reliable as a fingerprint on glass. There's something almost intimate about this. We can't touch stars. We can't visit them, not in any human time frame, but we can know them. We can read their compositions, trace their histories, predict their futures, all from light. And that light, traveling for years or centuries or millennia, carries the message intact. The information doesn't degrade. The spectral lines don't blur. A photon emitted from a star 1,000 light years away arrives here with the same wavelength, the same energy, the same encoded data it had when it left. Light is a time capsule and spectroscopy is the key. Now, here's a question you might not have considered. Why do we trust this? How do we know that the spectral lines we see in starlight actually correspond to the elements we think they do? The answer is experiments, lots of them. Scientists in laboratories on Earth have measured the emission and absorption spectra of every element, every ion, every molecule. They've cataloged millions of lines, created databases, refined the measurements to incredible precision. When we see a line in a star's spectrum, we compare it to the lab data. If it matches, we know what caused it. And the match is always exact down to fractions of a nanometer. The laws of physics don't change. Hydrogen here behaves the same as hydrogen in the Andromeda galaxy. The universe is consistent, and that consistency allows us to decode it. But spectroscopy reveals more than just static composition. It also shows us dynamics movement change. Some stars have spectral lines that split into multiple components, a phenomenon called Zeeman splitting. This happens when a star has a strong magnetic field. The magnetic field affects the energy levels of the atoms, causing single lines to split into two or three. By measuring the splitting, astronomers can calculate the strength of the magnetic field, even though the star is light years away. We're not just reading chemistry, we're reading physics magnetism, the invisible forces that shape stellar atmospheres. There's a star called Eta Carinae, a massive unstable supergiant surrounded by a nebula of ejected material. When astronomers study its spectrum, they see lines from hydrogen, helium, nitrogen, oxygen, iron, all shifted and split and broadened by the violent motion of gas in the nebula. The lines tell a story of chaos of a star tearing itself apart, flinging material into space at thousands of kilometers per second. The spectrum is a record of violence, a transcript of a star in crisis. And we can read it frame by frame, line by line. So, when you look at a star, any star, remember this. The color you see is just the surface. Beneath it, hidden in the light, is a language. A code written in wavelengths and absorption and emission in shifts and splits and shadows. Every star is speaking constantly, sending out its story in every photon. And we standing here on this small planet have learned to listen. We've cracked the code. We've turned light into knowledge. It's one of the most profound achievements of science, and it's still unfolding, still teaching us, still revealing secrets we didn't know were there. But stars don't just speak for themselves. They also paint the space around them, casting light and color across the void, illuminating clouds of gas that would otherwise be invisible. And those clouds, those nebulae, glow with colors of their own colors that reveal not just the composition of the gas, but the nature of the stars hidden within. Space isn't empty. We think of it that way, a perfect vacuum, a silent nothing between the stars. But look closer through a telescope with enough exposure time, and you'll see something else. Clouds. Vast glowing clouds of gas and dust, painted in colors so vivid they seem unreal. Red, green, blue, sometimes all three at once, swirling together like watercolors bleeding into each other. These are nebulae, and they're not glowing on their own. They're lit by stars energized by radiation so intense it strips electrons from atoms and makes the atoms scream in color. A nebula is, in the simplest terms, a cloud of hydrogen, helium, and trace amounts of heavier elements spread across light years of space. Some are stellar nurseries regions where new stars are forming, collapsing out of the gas under their own gravity. Others are stellar graveyards, the remnants of stars that have died shedding their outer layers into space. And a few are both places where death and birth happen side by side, where old stars explode and their debris seeds the formation of new ones. But regardless of their origin, nebulae share one thing in common. They glow. And the way they glow, the colors they emit, tells us exactly what's happening inside them. There are two main types of glowing nebulae, emission nebulae and reflection nebulae. Emission nebulae shine because the gas itself is emitting light. A nearby hot star, usually an O-type or B-type, floods the nebula with ultraviolet radiation. That radiation is energetic enough to ionize the hydrogen atoms, stripping away their electrons. When the electrons recombine with the hydrogen nuclei, they release energy as visible light. Specifically, they release it at very specific wavelengths, the same spectral lines we talked about before. The result is a nebula that glows red because hydrogen's brightest visible emission line, H alpha, is red, 656 nanometers. Always. Reflection. Nebulae work differently. They don't emit their own light. Instead, they reflect the light of nearby stars, scattering it the way Earth's atmosphere scatters sunlight to make the sky blue. The dust particles in the nebula are just the right size to scatter shorter wavelengths more efficiently than longer ones. Blue light scatters, red light passes through. The result is a nebula that glows blue, not because it contains blue gas, but because it's acting like a mirror for blue starlight. It's the same physics that gives us blue skies during the day and red sunsets in the evening. Scattering, refraction, light bending and bouncing through particles too small to see. Let's start with an example you can find in the winter sky if you know where to look. The Orion Nebula, also called M42, is one of the brightest nebulae visible to the naked eye. It sits just below Orion's belt in the region we call the Sword. Even without a telescope on a dark night, you can see it as a faint, fuzzy patch of light. But through a telescope or in long exposure photographs, it transforms. The nebula glows red and pink, with hints of green and blue scattered throughout. The red comes from hydrogen. The green comes from doubly ionized oxygen glowing at 507 nanometers, a color our eyes aren't great at detecting, but cameras capture beautifully. The blue comes from reflection starlight bouncing off dust particles embedded in the gas. At the heart of the Orion Nebula is a cluster of young hot stars called the trapezium. These stars are O-types and B-types less than 1 million years old, still surrounded by the gas cloud they were born from. They're pumping out ultraviolet light at an incredible rate, ionizing the hydrogen around them, making it glow. Without those stars, the nebula would be invisible, a dark cloud blocking the stars behind it. But with those stars, it becomes a beacon, one of the most studied objects in the sky, a laboratory for understanding how stars and planets form. Here's something that surprises people. The colors you see in nebula photographs aren't always the colors you'd see if you looked through a telescope yourself. Human eyes aren't sensitive enough to pick up faint colors in dim light. The rods in your retina, the cells that work in low light, don't detect color well. So, when you look at the Orion Nebula through a backyard telescope, you'll see it as grayish-white, maybe with a hint of green, if the nebula is bright and your eyes are well adapted to the dark. The reds and blues and intricate details only appear in long exposure photographs, where the camera sensor accumulates light over seconds or minutes, building up color information that our eyes simply can't gather in real time. But the colors are real. They're not invented. They're not false. They're just too faint for our biology to perceive without help. Cameras extend our vision. They let us see the universe as it actually is, not as our eyes limit it to be. And what we see when we let the camera look long enough is a cosmos drenched in color. Let's talk about another nebula one with a very different story. The Ring Nebula, also called M57, is a planetary nebula in the constellation Lyra. Planetary nebulae have nothing to do with planets, by the way. The name is a historical accident. Early astronomers looking through primitive telescopes thought these round disc-like nebulae resembled planets. The name stuck even after we realized they're actually the outer shells of dying stars puffed off into space during the red giant phase. The Ring Nebula is the remnant of a star, much like our sun. About 10,000 years ago, that star exhausted its core, hydrogen swelled into a red giant, and then began shedding its outer layers in gentle pulses. The core, now exposed, is incredibly hot, around 100,000 degrees, glowing blue-white. The ultraviolet light from that core ionizes the surrounding shell of gas, making it glow. The shell expands outward at about 20 kilometers per second, a slow crawl by cosmic standards, and as it expands, it cools and fades. Right now, the Ring Nebula is bright enough to see through a small telescope. In a few tens of thousands of years, it will have dispersed completely, blending back into the interstellar medium invisible. The Ring Nebula glows in multiple colors. The inner regions closest to the central star glow blue and green, dominated by helium and oxygen emission. The outer regions glow red, dominated by hydrogen. This color gradient isn't random. It reflects the temperature and density structure of the nebula. The hottest, densest regions close to the star ionize heavier elements like oxygen. The cooler, more diffuse outer regions only ionize hydrogen. The nebula is a layered onion of chemistry, and each layer glows in its own color. There's another famous nebula, the Crab Nebula, which has a completely different origin. The Crab is a supernova remnant, the leftover debris from a massive star that exploded in the year 1054. Chinese and Arab astronomers recorded the event. They described a new star appearing in the sky, bright enough to be visible during the day for several weeks. That was the supernova. What we see now, nearly 1,000 years later, is the expanding cloud of gas ejected during the explosion, still glowing, still moving outward at thousands of kilometers per second. The Crab Nebula glows in a chaotic mix of colors: red from hydrogen, blue from synchrotron radiation, a type of light emitted by electrons spiraling through magnetic fields at near-light speeds. The synchrotron emission comes from the nebula's central pulsar, a rapidly spinning neutron star left behind by the supernova. The pulsar spins 30 times per second, emitting beams of radiation like a lighthouse, energizing the gas around it, keeping the nebula bright. Without the pulsar, the Crab would have faded by now. But the pulsar is still pumping energy into the system, and so the nebula continues to glow, a monument to violent death. Let's address a common misconception. People see these images, these vibrant reds and greens and blues, and assume they've been artificially colored, that astronomers are adding hues for aesthetic purposes. Sometimes that's true. Some nebula images use false color, where different wavelengths of light, including infrared and ultraviolet, are mapped to visible colors so we can see them. But many images, especially those taken in visible light, are showing real colors. The red is really red. The green is really green. The blue is really blue. The issue is just that our eyes looking through a telescope can't accumulate enough light to see those colors clearly. The camera does what our eyes can't. It integrates photons over time, building up the signal until the color becomes visible. There's a nebula called the Horsehead Nebula, a dark silhouette against a background of glowing red gas. The horsehead itself doesn't glow. It's a dense cloud of dust and molecular hydrogen too cold and thick to emit light, blocking the red H-alpha emission from the gas behind it. The shape a horse's head in profile is pure coincidence, a random arrangement of dust, sculpted by stellar winds and radiation pressure. But that red background, that glowing backdrop, is an emission nebula energized by a nearby star. The contrast between the dark dust and the bright gas creates one of the most striking images in astronomy, a reminder that space is full of shadows and light, emptiness and density, silence and color. Some nebulae glow in colors we can't see at all. The Helix Nebula, another planetary nebula, emits strongly in infrared light wavelengths longer than red, invisible to human eyes. Infrared reveals warm dust regions where molecules are forming, places where the nebula is cooling and coalescing. Astronomers use infrared telescopes like the James Webb Space Telescope to peer into these hidden layers, to see the chemistry happening in the dark. And what they find is astonishing. Complex molecules, carbon chains, organic compounds, the building blocks of life forming in the remnants of dead stars. The colors of the infrared translated into visible hues show us a universe that's not just glowing, but creating, assembling new structures out of old ashes. Let's talk about the pillars of creation, arguably the most famous image ever taken by the Hubble Space Telescope. The pillars are part of the Eagle Nebula, a massive star-forming region about 7,000 light-years away. The image shows three towering columns of gas and dust, each several light years tall, silhouetted against a background of glowing red and orange. The pillars are being eroded by radiation from nearby massive stars, slowly evaporating, sculpted into these dramatic shapes by the pressure of starlight. At the tips of the pillars, you can see small knots of denser material, protostars, stars still forming cocooned in gas. The colors in the pillar's image are real, but they've been enhanced to bring out detail. The red comes from sulfur emission. The green comes from hydrogen. The blue comes from oxygen. Each color represents a different layer, a different chemical signature, revealing the structure of the nebula in 3 dimensions. The image isn't just beautiful, it's scientific. It's a map, a visualization of chemistry and physics happening on a scale so vast, it's hard to comprehend. And it's happening right now, as you read this as you breathe. Stars being born in pillars of gaslight, painting the void in colors we've learned to see. Here's a question you might not have considered. Do nebulae fade over time? The answer is yes, but slowly. An emission nebula glows as long as the central star keeps pumping out ultraviolet light. When the star dies or moves away, the nebula fades, recombining, cooling, becoming invisible. A supernova remnant like the Crab will glow for thousands of years, maybe tens of thousands energized by its pulsar. But eventually, even the pulsar will slow down, the synchrotron emission will weaken, and the nebula will dim. A planetary nebula like the Ring disperses, expands, thins out until there's not enough gas left to glow. The colors don't last forever. They are temporary, a brief phase in the endless cycle of stellar birth and death. But while they last, they're messages. They tell us what stars are made of, how they die, what they leave behind. The red of hydrogen, the green of oxygen, the blue of scattered starlight. Each hue a clue, each shade a story. And all of it, every photon, every color comes from stars. Stars that are either lighting the gas or have already died and left it glowing. Stars that paint the void, that turn emptiness into something visible, something beautiful, something we can study and understand. It's worth remembering that most of the universe is dark. Most of space is empty, unlit, invisible. But in these scattered pockets, these nebulae light wins. Gas glows, color appears. And we, from our distant vantage point, get to witness it. We get to see the universe painting itself using stars as brushes and atoms as pigment. It's a slow painting, one that takes millennia to complete, but it's still being painted. And we're here watching, learning to read the colors, learning to understand the language written in light. Yet, even as we decode these cosmic canvases, we must remember that the colors we perceive are filtered through our own biology, shaped by the quirks of human vision. And that raises a deeper question. Are we seeing the universe as it truly is, or only as our eyes allow us to see it? Your eye is a liar, not maliciously, not intentionally, but it lies nonetheless, filling in gaps, smoothing over inconsistencies, translating the raw data of light into something your brain can process. And nowhere is this more obvious than when you look at the stars. What you see isn't what's there. It's an interpretation, a best guess, a translation filtered through biology that evolved not to perceive truth, but to survive. The stars are sending accurate information. Your eye is rewriting it. Let's start with the architecture of vision, because understanding what you see requires understanding how you see. The back of your eye, the retina, contains 2 types of photoreceptor cells, rods and cones. Rods are sensitive to dim light, but don't detect color. Cones detect color, but need relatively bright light to function. You have about 120 million rods and only about 6 million cones, and they're not evenly distributed. The cones are concentrated in the center of your vision in a small pit called the fovea. The rods dominate the periphery. This means that in bright light, when your cones are active, you see the world in full color. In dim light, when only your rods are working, the world fades to grayscale. Now, when you look at a faint star, you're relying almost entirely on your rods. The light from the star isn't bright enough to activate your cones, so you see the star as white or grayish, even if it's actually red or blue. Bright stars like Betelgeuse or Rigel emit enough light to trigger your cones, and you can see their colors. Betelgeuse looks reddish-orange. Rigel looks blue-white. But fainter stars, stars that are objectively just as colorful, appear colorless to you. Not because they lack color, but because your eye lacks the sensitivity to perceive it. This creates an interesting paradox. The Pleiades, a star cluster in Taurus, contains hundreds of blue stars. If you photograph them, they show up vividly blue, a striking contrast against the black sky. But if you look at them through binoculars or a small telescope, most of the stars look white. Only the very brightest, like Alcyone and Atlas, show a hint of blue. The rest are too faint. Your rods see them. Your cones don't. The color is there in the light, but your biology won't let you see it. Here's where it gets stranger. Even when your cones do activate, even when you see color, your brain is still editing the signal. There's a phenomenon called chromatic adaptation, or white balance, where your brain adjusts the colors you perceive based on the surrounding light. If you're indoors under warm, incandescent lighting, your brain compensates, making white objects still look white, even though they're bathed in yellowish light. If you step outside into daylight, which is bluer, your brain compensates again, shifting the white point. This is why photographs taken indoors without a flash often look orange. The camera isn't adjusting the way your brain does. It's showing the light as it actually is. The sun is a perfect example. From space, the sun appears white maybe, with a very faint yellow tint, but essentially white. It emits light fairly evenly across the visible spectrum, peaking in the green-yellow range, but covering all colors. Yet, from Earth we see it as yellow, sometimes orange, especially near the horizon. Why? Because Earth's atmosphere scatters blue light more efficiently than red light, removing some of the blue from the sun's spectrum and making it appear warmer. But even beyond that, your brain is adjusting. It's taking the incoming light, comparing it to the blue sky, and deciding that the sun is yellow. The sun hasn't changed. Your perception has. Let's conduct a thought experiment. Imagine you could turn off your brain's white balance. Imagine you could see light exactly as it hits your retina, with no adjustment, no compensation. The sun would look whiter. Indoor lights would look more orange. Stars would look subtly different, less uniform, more varied in hue. You'd see the world as a camera sees it raw and unfiltered, but you'd also struggle to function. Your brain edits the world because raw sensory data is overwhelming, chaotic. Editing helps you focus on what matters. But it also means you're never seeing objective reality. You're seeing a curated version, a translation. There's a historical figure who understood this limitation better than most. Hermann von Helmholtz, a 19th century German physician and physicist, studied the physiology of vision in extraordinary detail. He dissected eyes, measured the response times of photoreceptors, calculated the limits of human color perception. He realized that what we call color isn't a property of light itself, but a property of how our brain interprets different wavelengths. Light at 700 nanometers isn't inherently red. It's just electromagnetic radiation vibrating at a certain frequency. Our brain assigns it the label red. If our eyes were built differently, if our photoreceptors were sensitive to different wavelengths, we might see that same light as something else entirely, or not see it at all. Some animals see colors we can't. Mantis shrimp, for instance, have 16 types of color receptors compared to our 3. They see a spectrum. We can't even imagine colors that don't have names because we have no reference for them. Birds see ultraviolet light. Flowers that look plain white to us are covered in UV patterns visible to bees and hummingbirds guiding them to nectar. The universe is full of colors. We're blind to information we're missing simply because our biology didn't need to detect it. We evolved to see what helped us survive, not what's true. Now let's talk about telescopes and cameras because they reveal the limitations of our eyes in stark detail. A modern CCD camera, the kind used in astronomy, can detect light far fainter than the human eye. It can accumulate photons over minutes or hours, building up a signal where our eye would see nothing. It can separate wavelengths with precision, capturing red and blue and green independently, then recombining them to show the true color of an object. And it doesn't have rods and cones. It doesn't have chromatic adaptation. It sees what's there. The Hubble Space Telescope, for example, doesn't take color photographs. It takes grayscale images through different filters, each filter allowing only a narrow range of wavelengths to pass. One image in red light, one in green, one in blue, sometimes in ultraviolet or infrared as well. Those images are then combined, assigning each wavelength a color, creating a composite image. If the filters correspond to visible light, the result is close to what you'd see if your eyes were sensitive enough. If the filters include invisible wavelengths, the result is false color, but it's still real data, just translated into a form we can perceive. Let's take the famous Pillars of Creation image again. Hubble captured it using filters for sulfur, hydrogen, and oxygen emission lines. Sulfur was mapped to red, hydrogen to green, oxygen to blue. The result is an image that's scientifically accurate, but not necessarily what you'd see if you were there. If you could travel to the Eagle Nebula and look at the pillars with your own eyes, you'd probably see them as faint, grayish-green smudges because your rods would dominate your vision and your cones wouldn't gather enough light to show the full color. The Hubble image isn't fake, it's enhanced. It's showing you what's really there in a way your eyes could never manage on their own. There's a common misconception that these images are photoshopped, that astronomers are inventing colors to make things look prettier. Sometimes, yes, artistic choices are made. Color saturation might be increased to bring out faint details. Contrast might be adjusted to reveal structure. But the underlying data is real. The wavelengths are real. The emissions are real. The colors are just being translated, shifted into a range we can see and appreciate. It's no different from translating a book from another language. The words change, but the meaning remains. Here's another limitation of human vision: dynamic range. Your eye can adapt to a wide range of brightness levels, but not simultaneously. If you look at a bright light and then look away, you see an after image, a ghost burned into your retina. If you try to look at something very bright and something very dim at the same time, you struggle. Your eye adjusts to one or the other, but not both. Cameras have a similar problem, but they handle it differently. You can take multiple exposures, one for the bright parts, one for the dim parts, and combine them. This is called HDR, high dynamic range imaging. It's a way of seeing more than your eye can see in a single glance. When astronomers photograph a star cluster, they often use HDR techniques. The bright stars would normally saturate the image, washing out the faint stars. But by taking a short exposure for the bright stars and a long exposure for the faint ones, they can show both in a single image. The result reveals the full population of the cluster, from the brilliant blue giants to the dim red dwarfs, all in their proper colors. Your eye can't do that. If you look at a cluster through a telescope, the bright stars dominate and the faint ones fade into the background. The camera corrects for that limitation. Let's address something subtle but important: the Purkinje effect. As light levels drop and your vision shifts from cone-dominated to rod-dominated, your sensitivity to different colors changes. In bright light, your eye is most sensitive to yellow-green, around 550 nanometers. This is why yellow safety vests and highlighters are so visible. But in dim light, your peak sensitivity shifts to blue-green, around 500 nanometers. Red objects which look bright in daylight become darker. Blue objects which look dim become relatively brighter. This means that if you look at a star cluster at twilight, as the sky darkens, the red stars will seem to fade faster than the blue stars, even though both are emitting the same amount of light. Your perception is shifting, not the stars. Johannes Purkinje discovered this effect in the early 1800s, long before anyone understood the biology behind it. He noticed that red flowers in his garden looked bright during the day but appeared nearly black at dusk, while blue flowers remained visible longer. He didn't know about rods and cones, but he documented the phenomenon carefully. It's a reminder that even something as simple as color perception is more complex than it seems. Your eye isn't a passive receiver, it's an active interpreter, constantly adjusting, constantly filtering. Now, here's a question. If our eyes are so limited, so prone to error, why did they evolve this way? The answer is efficiency. Color vision is expensive. It requires multiple types of photoreceptors, complex neural processing, and a lot of energy. Our ancestors needed to see well enough to find food, avoid predators, and recognize faces. They didn't need to see the faint colors of distant stars. So, evolution optimized for what mattered. We got 3 types of cones giving us trichromatic vision, decent but not exceptional. We got rods for night vision monochrome but sensitive. And we got a brain that fills in the rest, making educated guesses to create a coherent picture of the world. But that picture is incomplete. We see a narrow slice of the electromagnetic spectrum from about 380 to 750 nanometers. Below that is ultraviolet. Above that is infrared. Both invisible to us, but not to instruments. Infrared cameras reveal heat signatures, warm objects glowing in the dark. Ultraviolet cameras reveal fluorescence materials that absorb UV light and re-emit it as visible light. The universe is full of information we're missing simply because our eyes weren't built to detect it. Astrophotography is, in a sense, an act of rebellion against our biology. It's saying I refuse to accept the limits of my vision. I want to see more. And through long exposures, sensitive sensors, and careful processing we do. We see nebulae glowing in colors too faint for the eye to detect. We see galaxies billions of light years away, their light redshifted into wavelengths we can barely perceive. We see the cosmic microwave background, the afterglow of the Big Bang, mapped not in visible light, but in microwave radiation, translated into false color so we can comprehend it. There's something humbling about this. The universe doesn't care if we can see it. It exists glowing and radiating regardless of our perception. Stars are blue or red or white whether we notice or not. Nebulae glow in hydrogen red and oxygen green whether our eyes can detect it or not. The truth is, they're constant indifferent. We're the ones struggling to keep up building tools to extend our senses to see what evolution didn't prepare us for. And yet, despite all these limitations, we've learned so much. We've mapped the colors of stars, decoded their spectra, understood their life cycles, all by carefully compensating for the quirks of human vision. We've built instruments that see better than we do, and we've trusted those instruments even when they contradict our intuition. That's science. That's the willingness to look beyond what feels true and ask what actually is true. So, when you look up tonight, remember this. The stars you see are not the stars that exist. They're the stars your eye allows you to see, filtered through rods and cones, adjusted by your brain, limited by biology. But the real stars, the true stars, are out there shining in their full spectrum, waiting for those who build the tools to see them. And what those tools reveal is more than just color. They reveal a pattern, a structure, a living map of the universe written in light. That map is what we turn to next. Color is not decoration. It never was. Every shade, every hue, every subtle shift, from blue to red, carries information encoded billions of years ago. Information that's still traveling toward us, still waiting to be read. When you look at the night sky and see stars in different colors, you're not just seeing variety, you're seeing history. You're seeing a map, a living chronicle of the universe written in wavelengths of light. And if you learn to read that map, if you learn to trace the patterns hidden in the colors, you begin to see something extraordinary. The cosmos isn't static, it's evolving, growing, changing, and the colors tell you how. Let's start with something simple. A single star burning alone in the dark. Its color tells you 3 things immediately. First, its temperature. Blue means hot 30,000 degrees or more. Red means cool 3,000 degrees, maybe less. White or yellow means somewhere in between. Second, its age, at least roughly. A blue giant is young, burning fast, living recklessly. A red dwarf is either very young and will stay red forever, or very old, a giant that swelled and cooled in its final years. Third, its fate. Massive blue stars will explode. Small red stars will fade slowly. Mid-sized stars like the sun will swell shed and leave behind white dwarfs. Color is prophecy. It tells you where a star has been and where it's going. But stars don't exist in isolation. They gather in clusters and galaxies and vast structures that span millions of light years. And when you zoom out, when you look not at individual stars, but at populations, the colors become even more revealing. A galaxy glowing blue is forming stars actively, aggressively turning gas into new suns at a rate that won't last forever. A galaxy glowing red is quiet, settled full of old stars that have already burned through their youth. The color of a galaxy is the color of its history. Take the Andromeda Galaxy, the nearest large spiral galaxy to the Milky Way. In photographs, Andromeda's spiral arms glow blue dotted with bright blue knots where massive stars are being born. The core, by contrast, glows yellow-white dominated by older, cooler stars. This color gradient tells a story. The arms are young, still forming stars from clouds of gas. The core is old, its star formation, mostly finished its gas, used up or blown away. If you could watch Andromeda over billions of years, you'd see the blue fade as the massive stars die, and the galaxy would slowly shift toward red, becoming quieter, older, a relic of its former self. Now, compare that to an elliptical galaxy, something like M87 in the Virgo cluster. M87 is red, deeply red. It stopped forming stars billions of years ago. All its blue giants are gone, exploded, or collapsed into neutron stars and black holes. What remains are red dwarfs, orange giants, ancient stars, slowly cooling. The galaxy is a graveyard, beautiful in its stillness, but no longer creating. The color red in this context doesn't mean heat. It means silence. It means the end of an era. Scientists suggest that this color difference, blue galaxies versus red galaxies, reflects a fundamental divide in the universe. Blue galaxies are still evolving, still churning out stars, still dynamic. Red galaxies are finished, or nearly so, coasting on the momentum of their past. And between them is a population called the Green Valley galaxies in transition, moving from blue to red as their star formation slows and stops. The Green Valley is a kind of purgatory, a phase that doesn't last long in cosmic terms, a few 100 million years at most. Galaxies pass through it, quickly shifting from youth to old age, without lingering in between. But color reveals more than just age and activity. It also reveals motion. This is where redshift and blueshift come in the Doppler effect applied to light. When a star or galaxy moves away from us, its light stretches shifting toward longer wavelengths, toward the red end of the spectrum. When it moves toward us, its light compresses, shifting toward the blue. The shift is usually small, too subtle to see by eye, but spectrographs can measure it with incredible precision. And what those measurements revealed, starting in the 1920s with Edwin Hubble's observations, was astonishing. Hubble noticed that almost every galaxy he observed was redshifted. Not just a few, not just the distant ones, nearly all of them. And the farther away a galaxy was, the greater its redshift. This wasn't random, it was systematic. It meant that galaxies weren't just moving away from us. They were moving away from each other. Space itself was expanding, stretching, carrying galaxies apart like dots on an inflating balloon. The universe, Hubble realized, had a history. It had been smaller once, denser, hotter, and it was still growing. This discovery, born from reading the colors of light, from measuring tiny shifts in spectral lines, changed everything. It gave us the Big Bang, the understanding that the universe had a beginning, that it's been evolving for 13.8 billion years, and that it's still evolving now. The colors didn't just tell us what galaxies are made of or how old they are. They told us the universe itself has a story, a narrative arc from hot, dense plasma to the cold, scattered stars we see today. Let's make this tangible. Imagine you're looking at a quasar, one of the most distant objects we can observe. Quasars are supermassive black holes actively feeding on gas, radiating enormous amounts of energy. The quasar you're looking at is 12 billion light years away, so you're seeing it as it was 12 billion years ago, less than 2 billion years after the Big Bang. When you measure its spectrum, you find that the light is massively redshifted. Lines that should appear in the ultraviolet are stretched all the way into the visible range. Lines that should be blue are shifted to red. The quasar isn't just moving away. It's receding at a significant fraction of the speed of light, carried by the expansion of space itself. That redshift tells you how far away the quasar is, how long ago the light was emitted, and how much the universe has expanded since then. It's a timestamp, a receipt, a piece of evidence that the universe was once much smaller and has been growing ever since. The color, that deep redshift, is a fossil. It's ancient information preserved in light, still readable, still telling its story, after traveling for most of the universe's history. Now here's something surprising. Not all galaxies are redshifted. A few, the very closest ones, are blue-shifted. Andromeda, for instance, is moving toward us, not away. Its light is shifted slightly toward the blue, indicating that it's approaching at about 110 kilometers per second. Why? Because Andromeda and the Milky Way are gravitationally bound. They're orbiting each other slowly. And in about 4 billion years, they will collide, merging into a single larger galaxy. The blue shift is a warning, a prediction written in color telling us what's coming, even though it's billions of years away. There's a deeper layer to this. When astronomers look at the most distant galaxies so far away their light has been traveling for over 13 billion years, they find something strange. Those galaxies are smaller, messier, more chaotic than nearby galaxies. They're blue-rich in young stars, but they're also irregular, lacking the elegant spiral or elliptical shapes we see in mature galaxies. This makes sense. We're seeing them as they were in the early universe before they had time to settle, before collisions and mergers shaped them into the structures we recognize today. The color blue in this context means youth not just for individual stars, but for the galaxies themselves. It means we're looking back in time, watching the universe assemble itself, star by star, galaxy by galaxy. Color is also a map of chemistry. In the very early universe moments after the Big Bang, there were no heavy elements. No carbon, no oxygen, no iron. Only hydrogen and helium with trace amounts of lithium. The first stars, called population 3 stars, were made entirely of these primordial elements. They burned hot and blue, massive and short-lived. And when they exploded as supernovae, they seeded the universe with the first heavy elements. Those elements became part of the next generation of stars, which burned, fused more elements, and exploded again. Each generation enriched the cosmos, adding carbon, nitrogen, oxygen, silicon, iron, all the elements that make planets' atmospheres and life possible. When astronomers analyze the spectra of old stars that formed early in the galaxy's history, they find very few heavy elements. These stars are called metal poor, and their spectra reflect that. The absorption lines for elements like iron and calcium are weak or absent. Younger stars, like the Sun, are metal-rich. Their spectra show strong lines from heavy elements. The color of the light doesn't change much, but the details in the spectrum tell the story of chemical evolution of a universe slowly building complexity out of simplicity. There's a star called Xi 1523 Neuro 9C1, one of the oldest stars ever discovered. It's about 13.2 billion years old, formed when the universe was only 600 million years old. Its spectrum shows almost no heavy elements, confirming that it came from an early generation before the galaxy had been enriched by many supernovae. The star is red, a red giant, now nearing the end of its life. But the fact that it's still here, still glowing, tells us something profound. The universe is old enough to have stars that have lived almost as long as the cosmos itself. And we can identify them, date them, understand them all by reading the colors and lines in their light. Let's step back and think about what this means. Every time you look at the sky, you're seeing a map. The blue regions are young, the red regions are old or cooling. The spectra tell you what things are made of. The redshift tells you how far away they are and how fast they're receding. The brightness tells you how much energy they're emitting. All of this, every piece of information, is encoded in light. And light, patient and tireless, carries it across the void, across billions of years, until it reaches us. We've learned to read that light. We've built spectrographs and photometers and telescopes, instruments that can measure wavelengths to fractions of a nanometer, that can detect photons from objects so distant their light left before the sun was born. We've learned to decode redshift, to trace the expansion of the universe, to map the distribution of galaxies across cosmic time. And all of it starts with something as simple as color: blue, red, green, yellow. The same colors you see in a rainbow, just stretched across distances and time scales that defy comprehension. Here's a thought experiment. Imagine you could see the universe not as it is now, but as it will be in 1 trillion years. The blue galaxies would be gone. Star formation would have ceased. The massive stars would have all died, and even the sun-like stars would be fading. The universe would be dominated by red dwarfs, tiny, dim, slowly burning through the last reserves of hydrogen. Galaxies would be redder, quieter, emptier, and the expansion of space would have carried most galaxies so far apart that they'd be invisible to each other, isolated beyond the reach of light. The universe would be cold, dark, and red. The color map would tell a story of ending of entropy winning, of a cosmos slowly winding down. But we're not there yet. We're here now in a universe that's still forming stars, still glowing blue, in places still dynamic and alive. And the colors we see, the blues and reds and whites scattered across the sky, are evidence of that life. They're proof that the universe is still working, still creating, still evolving. And we get to witness it. We get to map it. We get to read the light and understand the story it tells. So, when you look up tonight, see if you can shift your perspective. Don't just see stars as dots. See them as data points, each color a coordinate on a map of temperature, age, distance, composition. See the blue stars as young giants burning fast, pouring light into the cosmos. See the red stars as either patient dwarfs or aging giants depending on their brightness. See the white stars as balanced, steady somewhere in the middle. And see the galaxies, if you can find them, as populations, as communities of stars, their colors revealing whether they're still forming or slowly fading. The universe is not a mystery, not entirely. It's a puzzle, yes, but it's a puzzle that gives you the pieces. Every photon is a clue. Every wavelength is a hint. And if you're patient, if you learn the language, if you listen to what the light is saying, the puzzle starts to make sense. You begin to see patterns, connections, a story that's been unfolding for billions of years and will continue for billions more. Color is the key. It always has been. From William Herschel discovering infrared light, to Annie Jump Cannon classifying stars, to Edwin Hubble measuring redshift, to Cecilia Payne decoding stellar composition. Every breakthrough in astronomy has come from reading light more carefully, from paying attention to the colors and the details hidden within them. And that work continues. Right now, telescopes are observing the most distant galaxies ever seen, measuring their redshifts, mapping their colors, tracing the history of the universe back toward its beginning. And every measurement, every spectrum, every photon adds another piece to the map. You don't need a telescope to appreciate this. You don't need a degree in astrophysics. You just need to look up and remember that the light reaching your eyes has traveled sometimes for millions or billions of years, carrying information the whole way. That light is speaking, and now maybe you can hear it. You can see the blue and know it means heat, youth, violence. You can see the red and know it means coolness, age, patience. You can see the white and know it's balance, a star in its prime burning steadily. The universe is a living map of light, and you standing here reading that map are part of the story too. You're made of atoms forged in stars, atoms that were once part of blue giants or red supergiants scattered across space in supernovae, gathered into clouds, collapsed into planets, assembled into you. The colors of stars aren't just out there. They're in here in your bones, in your blood, in every cell. You are stardust, and the light you see is your ancestral glow, the remnants of fires that burned long before Earth existed. So, rest in that. Let it settle gently. The stars are not distant strangers. They're family. Their light is a letter written long ago addressed to anyone willing to read it. And you've read it. You've learned the language. You know now why stars have different colors and what those colors mean. Temperature, age, composition, motion, fate, all of it written in light, all of it waiting always for someone to look up and listen. Thank you for drifting with me through this quiet journey. Thank you for letting curiosity guide you, for sitting with these ideas, for wondering about the stars. There are so many more stories written in the night sky, so many more questions waiting to be asked, so many more colors waiting to be understood. And we'll explore them gently, one story at a time, whenever you're ready to listen again. Until then, when you see a star, remember, it's not just light, it's a message, a color, a voice, speaking softly across the void, saying, I am here, I am this hot, I am this old, I am made of this. And I will burn and change and fade, but while I last, I will glow. And maybe that's enough. Maybe it was always enough just to glow, just to send light into the dark, just to be seen. Sleep well, dream gently. The stars will still be there when you wake. Good night.